So the next paper is on inference and learning with probabilistic generating circuits by Juha, Harviainen, Vaidyanathan, Peruvemba. Okay, I will not try further. Mikko, Koivisto. And the presenter is Juha Harviainen.
Thank you. So, hi again, I'm still Juha Harviainen, and this time I'm presenting a joint paper with Vaidyanathan, Peruvemba, Ramaswamy from Technische Universität Wien and Mikko Koivisto from University of Helsinki. And our paper is titled On Inference and Learning with Probabilistic Generating Circuits. So again, I'll start with the introduction and then present our new faster inference algorithms and discuss some issues we found with learning these probabilistic generating circuits, and then conclude by discussing some future directions. So we have different classes of inference queries for probability distributions like marginal queries or most probable explanation queries. And tractable probabilistic models are models that are able to answer these kinds of queries in a time that is polynomial in the size of the model and the size of the query. And PGCs are a class of TPMs that are able to answer the marginal queries in polynomial time. So they encode a joint probability distribution of many binary variables as a circuit-like structure. So for example, we can have a probability generating polynomial, which essentially encodes such a probability distribution. So here we have this joint probability table, and for each joint variable assignment, there is a term in the polynomial corresponding to that, such that it contains the indeterminate of a corresponding variable if it's set to 1. So for example, we have this joint assignment 001 with probability 0.025, and in the polynomial there is this corresponding term 0.025 times Z3, because in the variable assignment we had x3 be equal to 1. So that's the only indeterminate in that term. And so these circuits have 4 kinds of nodes. So there are, in its leaves, there can be constant valued nodes or indeterminate nodes. And then the internal nodes can be either weighted addition with possibly negative coefficients, which differs from the typical probabilistic circuits. And then we have just a regular multiplication. And in the paper where these probabilistic generating circuits were presented, Zhang et al. Also showed that these support this polynomial time marginal inference. So the goal is to evaluate this probability of certain set of variables having value 1 and certain set of variables having value 0, despite this slide saying that they should be 1. But those variables in B should be 0. And the way they do this is that within the circuit, they assign specific values to these indeterminates. So if the value should be 1, then they assign an indeterminate t that is same for all variables in A. If the variable should be 0, they assign 0. And otherwise, if it can be either 1 or 0, they assign 1. So now our circuit represents a univariate polynomial. And after evaluating this circuit, they extract the coefficient of the term t to the power of the size of the A, the set of variables that should be 1. So as an example, if we want x2 be equal to 1 and x3 to be equal to 0, then we assign z1 to be 1, z2 be equal to t, and z3 to be equal to 1. And so, as you can see on the image on the right-hand side, after evaluating this at the root node of the circuit, we are left with this polynomial 0.3t plus 0.35. And then we want to extract this highest degree term from there and take its coefficient, and that 0.3 corresponds to this marginal probability. And a quick comment about the relationship of PGCs to other tractable probabilistic models. So there are essentially two main classes of TPMs. So there are probabilistic circuits such as sum product networks or arithmetic circuits. And then there are determinantal point processes that encode those probability distributions in determinants of a matrix. And PGCs are strictly more expressive efficient than both decomposable probabilistic circuits and determinantal point processes. And the above TPMs have also, the relationships between them have been also studied by Zhang et al. In another paper, which showed that they are, neither of them is a subset of each other. So for example, DPPs cannot model positive dependencies between the variables. So in our paper, we show three kinds of speedups for these marginal probability queries. But this is complicated by the fact that it is actually really hard to learn those PGCs because it is NP complete to detect whether they encode an invalid probability distribution, in the sense that there could be a negative coefficient or negative probability for some assignment, which is not allowed. But we managed to work somewhat find a workaround to this issue and sketch a framework that is, at least in theory, able to learn PGCs while avoiding this issue. So about faster inference, in the previous work, these marginal inference queries take time O, mn log n log n, where the m is the size of the circuit and n is the number of variables in it. And this time complexity follows from the fact that we do operations at most m times, and each of them is performed over polynomials of degree at most n. But even in general case, we can do a slightly better by remembering that after doing this assignment of the indeterminates, we are left with univariate polynomial, and univariate polynomial can be uniquely identified after evaluating it over multiple different points. So by evaluating this univariate circuit over at most n points, we can determine its coefficients uniquely by doing standard polynomial interpolation, and then it is easy to extract that desired coefficients from that representation. But in most cases, we are actually able to do much better. So we say that a circuit is decomposable if no indeterminate appears in both subcircuits of any multiplication gate. And that's also called the scopes of that multiplication gate. So in case that happens, we are able to compute the marginal probability just by tracking the highest degree coefficients. So there cannot be anything strange canceling out happening if we do this, unlike in the general case. And so we only track the highest degree coefficients, and like with the previous example, on the right-hand side, you can see that this, at the root node, this circuit has still the same probability, 0.3, as desired. Then there's the third case, which comes from the fact that we can actually, determinants of a matrix can also sometimes encode a probability generating polynomial, as is demonstrated here. And we show in our paper that such determinants actually support marginal queries such that we can compute them by evaluating a real valued determinant. And this means that we can apply any fast determinant computing algorithm on them. This has many technical details, but as an example here, if we want to have x1, x2, and x3 to equal 1 and x4 to equal 0, then we essentially want to extract the terms 2z1, z2, z3, as well as this z1, z2, z3, and z5 from this matrix. And therefore, we assign certain values to these indeterminates and zero out certain entries such that the permutations with non-zero value correspond to these desired terms. So there are multiple rules, but as an example, there is only one entry containing this variable z3, and we wanted x3 to equal 1. So each permutation needs to pass through that entry on the second row and second column, and therefore we zero out all other entries on that row and column to obtain those desired permutations. But the main problems come with learning, because we show that it is NP hard to check if a PGC encodes a valid probability distribution in the sense that it contains no negative probabilities. And we do not need to care about the normalization constant because it is easy to compute in a linear time and then apply to the circuit. So we only care about the negative coefficients here. And we show this by reducing SAT solving instances into a problem of finding a term with a negative coefficient. And therefore, if we would be able to find a negative coefficient, we would also have solved the corresponding SAT instance. But this is still verifiable for moderate size circuits, let's say of 25 variables, because there are at most to the power of 20 coefficients we need to check. And we can do that manually if we really need to. But this causes issues with larger networks or circuits. But we propose a workaround for this by suggesting learning so-called compound circuits that are PGCs that consist of many smaller subcircuits that are interlinked in a way that they can be verified independently of each other. And then we propose a Markov chain simulation method for learning the weights of this circuit. So the structure of the circuit remains constant over this simulation, but the weights change. So we initialize this chain with any feasible solution, where feasibility here means that it encodes a valid probability distribution up to a normalizing constant, and then pick a candidate solution from its local neighborhood and either reject or accept that candidate. And if we accept it, we move there, and otherwise we stay at the current solution. And we iterate this until some condition is satisfied. But again, the problem here is that each of these steps is an engineering task of its own. So for example, with initialization, how should we initialize the weights of this circuit? We can, for example, pick to make the weights be any positive real numbers so that it encodes a valid probability distribution up to a normalizing constant, but it isn't necessarily a good estimation of the probability distribution. Then when we take this move step, how do we define this neighborhood? We could, for example, take a small step towards the gradient of the likelihood or something like that, but then there could be an issue that we end up in a local minima or something like that. What should be the acceptance condition? Should we always accept it if it's valid, or should we somehow probabilistically check whether we jump there or not in some simulated annealing fashion? And the fourth question is, how long do we simulate this chain? And because of all these implementation details, we have left research, further studying them to future work. And so to conclude, we have showed that inference is really fast with PGCs, but learning them is really hard. And there's this interesting trade-off. But one could also consider if it's possible to somehow check the validity of these PGCs on fast on some classes of PGCs, or if it's fast to check somehow on average, like for most instances, it is easy to check them. Because if you, for example, consider integer linear programming or SAT solving, we have really efficient solvers for them, even though they are still, in theory, really hard problems. So it could be that something similar could be applied in this case as well. And again, thank you for your attention and see you at the poster session.
So I would like to invite the discussant, Yujung Choi.
Hi, my name is Yujung Choi, coming from Arizona State University. It's my pleasure to be here to discuss this very nice paper. So I put up some key takeaways as a reminder. So we first, the authors showed 3 efficient inference algorithms for computing marginals on PGCs. What I thought was especially nice is that we get this linear time algorithm for marginals on decomposable PGCs, just like we do for computing marginals on decomposable probabilistic circuits, even though PGCs are strictly more expressive than regular PCs. But then also we saw that, you know, with this expressiveness comes the hardness in learning, because for to check whether an arbitrary PGC structure or arbitrary PGC encodes a valid distribution is actually NP hard, right? So a couple of questions I had. First of all, I didn't see this mentioned in the paper, but I thought the inference algorithm using polynomial interpolation may have some opportunities for easier parallelization than the existing algorithm, because the all the point evaluations can be done in parallel pretty easily. So perhaps the author could comment on that. And again, as Juha mentioned, there's still the remaining work of actually implementing this and seeing how well it works in practice to learn PGCs. Especially, I wasn't sure, you know, how expensive the feasibility checks and rejecting infeasible solutions would be. Which brings me to my last question, which was, can we actually avoid the feasibility checks altogether? Because often we're not given an arbitrary structure, but we have a choice over the structure, or we would learn the structure as well. So can we actually learn structures that would guarantee that any parameterization would represent a valid distribution? For instance, the paper discussed some composition operations over PGPs. So can we actually apply them recursively with a very simple base case PGPs, so that the solution is guaranteed, or the resulting structure is guaranteed to be a valid distribution? Right. Yeah, then thanks, and congrats again to a very nice paper.
So thank you for the excellent questions and comments. About the parallelization, I think that's an excellent idea, and it could actually probably applied also when we are verifying the validity of these circuits. About this, how well this sketched learning approach works in practice, well, we don't know, because the issue is that there are so many implementation details and there's nothing to compare it against in PGC literature, because this is such a new class of models that we had to leave it out of the scope of this study. But well, it remains to be seen. But about these feasibility checks, I'm a bit skeptical. Like, these compound models use this composition idea by composing them from these smaller circuits that can be verified independently of each other. And actually, if we change only one of them, then we only need to check if that's valid, and the others remain still unchanged in their validity, assuming that the new change the change subcircuit is valid after the change. But my main worry is that if we make these subcircuits too small, then these models can lose their expressiveness in the sense that we may require exponentially large circuits to represent these probability distributions. So there's some trade-off, and it remains to be seen in future work.
Okay, thank you. We have time for a question. Okay, so I have a question. How do you decide about the circuits that you start with? How do you decide what is the size of the circuits when you are doing for the learning? I mean,
well, that's a good question, but because we didn't implement any learning method, and there isn't exactly any studies about learning these circuits. So I guess the good idea is to just start from somewhere, and then if it seems too hard, then decrease the size. And if it seems not expressive enough, then you increase the size, and then try to find a good trade-off between them, expressiveness and complexity of learning.
thank you very much. Let's thank the speaker again.